Welcome back, ladies and gentlemen. We're going to be continuing now with something a little beyond conversions. We did percent composition last time, and it's going to come up. Um, Now, unfortunately, this video is probably going to be a little bit longer. I've got a lot of examples I want to show you guys. I want to explain at least two concepts. We're going to be covering page 29, 30, and 31. So buckle up, because here we go. So 29 talks about what's called an empirical formula. Now, empirical is a weird word. It doesn't come up often in general conversation. If something is empirical, that means it's like, how to describe it? It's something that you have discovered by carefully analyzing something, by like study and by experiment in a way. In a way. Maybe I should look up the definition of that word. Either way. It says here that the empirical formula is the formula that gives the simplest whole number ratio of the atoms of each element in the compound. For example, H2O. The empirical ratio would be 2 hydrogens for every 1 oxygen. Now, why is this important? Well, you see, for the last several years, you guys have been learning how the laws of chemistry work, how you put together different elements into making compounds and molecules. And we've taught you things like ionic bonding and covalent bonding and the sharing of electrons and the transferring of electrons and how all of this stuff fits together. We didn't know that at first. What we knew was that we had stuff. We dig something out of the ground and go, gee, I wonder what this is. And we would break it into smaller and smaller pieces, much as Democritus ended up doing when he was talking about atoms. And when we cut them up into smaller and smaller pieces, we discovered that there were, of course, different elements. And we discovered that not only were there elements, but there were specific ratios of elements. There were like a certain number of each. The problem is that when you study something by what is called destructive analysis, meaning that you destroy it in order to understand it, you destroy it. Again, scientists bad at naming things. Or well, maybe good, depending on how you look at it. The point is this: when you destroy it, that means that you can no longer tell exactly what you were looking at. Now, by itself, this wouldn't be a problem if we could work with, say, one molecule of a particular compound, because we'd have like one molecule of water, we'd break it into its pieces and be like, this molecule of some unknown material has 1 oxygen and 2 hydrogens, so it must be made of 2 hydrogen and 1 oxygen. The problem is, as we discussed when we talked about the mole, we can't do that. We can't work with one atom, one molecule of something, because it's too small. So by definition, we work with mountains of the stuff, buckets of the stuff. And the problem with buckets of the stuff is that, well, taking the markers, for example, if I have this as my compound and it's got lots of little examples of my unknown elements, and I pull them all apart and I destroy them all, effectively taking all the caps off of all the markers and having them scattered all over the place, all across my table here in front of me, when I'm left over, I can go, okay, I have 5 caps. I have 5 markers. I don't know how many caps came with each marker. Maybe I luck out and I get it right. Red and red. Maybe I think, oh, these two go together and maybe this one too. There you go. There, I made a new molecule. Oops, it's not quite right, but it sort of works. Or I get it completely wrong and I'm like, wow, maybe this one's just by itself. And this is a problem because in the old days when we were first studying all these different compounds, or even in the new days when we're studying something new that we've never seen before, we don't necessarily know what it's going to be until we break it down and look at it. But when we do break it down, we end up with so many pieces that we're not sure how to put it back together. Except we have the empirical formula. So this particular lesson is a strange one. It's kind of like when we did isotopes. Like when we did isotopes and I was like, here are isotopes, they're an interesting thing, they're useful in very specific circumstances, but for the most part, we're not going to do much with it. And everyone's like, why? This is us showing you how very specific kinds of chemistry are done in order to decipher the unknown and figure out things that are otherwise invisible. Most chemists don't have to do this because most chemists work with things that we already understand. It's just how most chemistry is done. But if you are on the frontiers of chemistry, if you are exploring to find new unknown materials and unknown medicines and unknown things, like, I don't know, what's the recent topical thing? Life on Venus. There you go. Who knows? Then, what can that mean? You need to have the ability to decipher what's going on. 29 will show you how to do that. So, we have an example. Calculate the empirical formula for a compound whose percent composition is 58.8% carbon, 9.8% hydrogen, and 31.4% oxygen. What they're basically saying is that they took this mountain of stuff, they broke it into pieces, and then they counted how many pieces they had left over, and they found that of all the pieces, 58.8% was carbon, 9.8% was hydrogen, 31.4% was oxygen. But by itself, that doesn't answer the question of how do I put the pieces back together to make the thing. So now we're going to do that. Step 1. If you are only given percentages, assume that the total mass of the sample was 100. Why? Makes the math easier. You could have made anything. You can make it 2. I don't care. But 100 will make your life a lot easier. Trust me on that. Step 2. Find the number of moles of each element in the 100-gram sample. All right, so we're going to write down our information here. So we've got our percentage. The percentages were, you remember, all right, we'll put our element, I guess. Our elements were carbon, hydrogen, and oxygen. What we would call a hydrocarbon because it's got hydrogen and carbon in it. Again, with the chemist being bad at naming things. I know. So our percentages. We've got here 58.8%. This one was 9.8. Wait. Was it 9.8? Yes, it's 9.8. Good. Percent. And oxygen, 31.4%. Okay, so there's our percentage. We are now going to figure out what mass that is. The way we get the mass in this context is that we know it was out of a 100-gram sample, and we have a 58%. So what is 58% of 100? And we're going to get 58 grams of carbon, or 9.8 grams of hydrogen, or 31.4 grams of oxygen. This, of course, adds up to 100. Again, you could use any number here. You don't have to use 100. It just means that your numbers won't be nearly so nice, and it'll take you longer to solve it. It's fine, though. I mean, your call. If you want to do more work, I won't stop you. Actually, generally, most students want to do more work. They don't realize it, but they do. Okay. So now that we've got the mass of this whole thing, our next step, as it tells us in step 2, is find the number of moles of each element. So hopefully we've had a lot of chance to convert moles, and we can do that now. We know our molar mass. So our molar mass of carbon is 12.01 grams per mole. For hydrogen's 1.01 grams per mole. For oxygen is 16 grams per mole. Weird how that one manages to be a round, nice round number, isn't it? Okay, when you do this conversion, reminder, conversion matrix will be your friend in this regard. So conversion matrix time. We'll do at least one just to remind everyone how they work, although at this point I hope you've done a million conversions. So we end up with 58 grams of C. I want to get moles of C. We're going to put grams on the bottom, moles on the top, because I want to get rid of grams and get moles. 1 mole is equal to 12.01 grams, which means I would take out my trusty calculator, take 58 divided by 12.01. And this one will give us 4.83. So we're going to get 4.83 moles for carbon. And we're going to get basically 9.8 moles of hydrogen because it's 1, and that's basically 1. And we're going to get 1.96 moles of oxygen. Okay, cool. So everything up until that point was just basically a review of the stuff we've already done, right? I mean, we got a percent composition. We then turned it into some gram quantities. So this is like if we had a 100-gram sample, we would have had a pile of 58 grams of carbon when we finished. Then we used our grams per moles in order to get moles. Awesome. What do we do next? Step 3. Calculate the mole ratio of the elements. So what you do is you take the smallest possible number of the mole quantity and you divide every one of them by that number. What do I mean? Well, this is the smallest possible mole number. So we take the smallest mole and we're going to divide every one of these by 1.96. Now the reason we're doing this has to do with mathematics. We're basically trying to sort of turn this into a ratio of the various terms. This is the easiest way to do it. When you do that, you are going to get your mole ratio. I'm going to do it in another color. That's how important it is. We're going to get, for this first one, this is going to be 2.5. This one here is going to be 5, and this one is going to be 1. When you do the mole ratio, you're going to get numbers, like without decimal, he says while pointing to one that has a decimal, with only decimals that are going to be easy to work with, right? As opposed to 1.96, that's going to be a mess. 2.5, we can work with that. But how do we work with that? Well, this is where we start to assemble our empirical formula. Our empirical formula in this case will be carbon 2.5, hydrogen 5, oxygen 1. No, we're not done because obviously we need to get rid of that decimal. We can't have 2.5 carbon. So what do? It's the same trick we used when we were balancing equations. It says right here, since this is not the lowest whole number ratio, we must multiply each number by a value that will give us a number that is all of them being whole numbers. In this case, it's by 2. If I multiply everything by 2, I will get C5H10O2. This, and he covers up some of the numbers, this, there we go, is the empirical formula. This is the formula of this compound as best we understand it based on what we found. This particular formula would be, that's almost a sugar, I think. That might be something you could eat. Maybe. I'd actually have to look it up. I'm not sure what that one is. It's got 5 carbons. Sugar normally has 6, though. Oh well. So, that's how you do empirical formulas. It's pretty simple. I mean, it's a pattern. Like, you follow the steps, you get the answer. You take the percentage, you turn it into basically out of 100, which really just comes down to taking the percentage and putting grams instead of percent. It's really simple. Molar mass to convert it to moles, divide by the smallest mole, in this case it was this one, and that gives you some ratios, and then you make it into a whole number in order to make the whole thing work. That's it. That's page 29. I think you can see why it is, and we're going to continue on some other ones. But, let's take a look here. If you guys take a look on page 30, there are some examples. And you'll notice that the first one is 75% carbon, 25% hydrogen. Okay. We'll use the same table. Just going to erase one of the rows. We don't need oxygen anymore. Get out of here, oxygen. We don't need you. You're boring me. It tells us that 75% is carbon and 25% is hydrogen. All right. So 75 goes here, 25 goes here. That means, obviously, this turns into good old 75 grams and 25 grams. And again, the only reason that works is because we're assuming that the sample is 100. The reason we're making it 100, because then this becomes super easy. The grams per mole stays the same. We're still doing the same basic conversion. The difference is, of course, I am doing a different number. So I erase that one number. I put in my new one, which is 75 grams, and I find what the new mole amount is. So what moles am I dealing with in this question? Well, I already did the work. It is in your answer key. You guys can check the answer key whenever you want. And it says here that I got 6.25 and 25. Now you might look at that and go, whoa, that's crazy. Why am I getting so much hydrogen when it was only 25 grams? This is 75 grams. This is like 3 times bigger. But over here, when I do moles, I get 25 versus 6.25. Well, it's because carbon's really heavy. So even though it's got a lot of mass, there's not a lot of carbon to do that. 25 grams of hydrogen is literally 25 moles of hydrogen, because hydrogen only has a mass of 1. All right, so we do that. Now, when we divide by the smallest number, which in this case is the carbon. Divide by 6.25 for both of them. When I do that, I'm going to get my whole number, my mole ratio. And I got here that it is 1 to 4. So my empirical formula is going to look like 1 to 4. These are both whole numbers. I don't have to multiply by anything. There's no decimals for me to get rid of. So the final answer here is going to just simply be CH4, because we don't normally put ones. That one I do recognize. That's methane. Yeah, like cows and stuff. We'll learn more about methane in the organic chemistry unit, by the way. But that's quite a ways from now. Anyway, that's how you do it. Now, there's another example on page 30, and this one actually makes things even easier for you because it tells you not percentages, actual gram amounts. So rather than start us here, it starts us here. We get to skip a whole step, and then the rest of it we follow through. See what you can do to figure that one out. You've got the answers, of course, that you can check. Right now, though, I'd like to continue on with page 31, molecular formulas. Empirical formulas, molecular formulas, what's going on here? Well, let's take a look. It says here, molecular formula is the formula that gives the actual number of atoms of each element in a molecular compound. The molecular formula is always a whole number multiple of the empirical formula. What do I mean by that? Well, let's go with a simple example. If I give you, let's say, yeah, that's a good one. The one they show right here is a series of tables. And they show you, for example, if I give you CH2, right? If I work it out in empirical formula and I find that for every 1 carbon, I have 2 hydrogens. That's an empirical formula that I could calculate. If I have that, well, there are lots of different ways that I could use this and still be true. What do I mean? Well, I could have this ratio of 1 carbon for 2 hydrogen, right? I could have this ratio if I did C2H4 or C3H6. Both of them have the same ratio, right? Because this would be 2 versus 4, which is the same as 1 to 2. This one is 3 to 6, which is the same as 1 to 2. So even though these are very different chemicals, they have the same ratio of pieces. This boils down to what I was saying about we didn't know what the different chemicals were at first. And when we broke them down with destructive analysis, we had so many pieces left over, we didn't know exactly how they went back together again, right? I could take this sample, break it into pieces, count up all the pieces and go, must be this. Why? Because, well, I could just have more individual molecules, but each molecule has less pieces in it because they both have the same basic ratio. That's a problem, because if the best you can do is everything that is 2 to 1 could be this, that's a lot of stuff, right? Like I just did 2 to 4, 3 to 6. I could keep going. The example in the book goes 20 to 40. I could have this C20, H40, right? I could have this giant mountain of carbon and hydrogen, and it just turns out to all be the same single molecule, or it could be thousands upon thousands of smaller molecules, and they'd all give me the same result. So what can I do? How can I figure this out? Well, the trick that you use is that you don't destroy all of your sample. You keep just a little bit left over. Why does this help? Because then you can compare the ratio with what you originally started with, and you can try to figure out how to make the two match. It tells you right here. To determine the molecular formula, we compare the molar mass of the unknown with the molar mass of the empirical formula, aka the fragment. The equation it shows is pretty much a percentage calculation. You end up with the unknown divided by the empirical. It's in your notes. So let's do an example. This is very complicated when it's very nebulous. The example, it says here glucose has an empirical formula of C1H2O. Okay, so we're going to do C1H2O. We're working with glucose, otherwise known as sugar. Everyone loves sugar. What else does it say? The experiment shows that its molar mass is 180 grams per mole. Okay, so we also know that whatever this thing is, it's got a molar mass. Let's not get too lazy here. We haven't gotten that far in the unit. Molar mass of, 180 grams per mole. Okay. What is the molecular formula? So that's the empirical formula. What's the molecular formula? Well, in order to figure it out, the first thing we have to do is figure out what the mass of that is, right? So we've got a carbon, 2 hydrogens, and an oxygen. All right, well, we know how to do that. Carbon, we'll do it in green, sure. Carbon is, of course, 12.01. There's only one of them. Hydrogen is 1.01, but there's 2 of them. And oxygen is 16.00, and we add all that up. When we do that, we get 30.03 grams. So what I'm saying is this fragment, this piece that we know it's this piece in some way. We just don't know how many. Is it 1 of these? Is it 2 of these? Is it 10 of these? But we know this piece weighs 30. We also know how heavy the whole thing is. There's a connection between these two. The question is just what is it? Well, the way we solve that is that we take the 180 of the molar mass, so the molar mass, and we divide it by the empirical mass. So what do we get? We're going to get 180 divided by 30.03. When you put that together and you divide it all out, you're going to get 6. What does that mean? That means that to make this, you need 6 of these. That's literally what division is. To make this, you need 6 of these. Well, these are this fragment. So I'm telling you there are 6 of those fragments put together to make glucose. Okay, well, if there are 6 of those fragments, that means I go CH2O and I multiply the whole thing by 6. So what am I going to get? I'm going to get C6H12O6. And there we go. This is the molecular or chemical formula for glucose. We found it because we were able to first analyze the sample of glucose in a fancy machine that we don't have here, but somebody has it. And they figured out that this is the component parts. And they figured out that this is the ratio of those component parts. It's always 1 to 2 to 1. Then they figured out, because they kept some of the sample left alive, that this is 180. Whatever it is, the whole thing is 180. So then the last step is, well, how many times does this go into this? So they worked it out. They figured out it's 6. So there are 6 of these attached together like Lego bricks to make glucose. Ta-da! We now know the structure of glucose. And it is only after we did this very thing, studying multiple different chemicals over many years, like we're talking decades, if not centuries in the case of some chemicals, not individual chemicals, but like suites or like sets of chemicals. It's only after studying them for a really long time that we were able to get enough understanding of the underlying patterns to develop the rules that we have since taught you in grade 9, 10, and now 11. All of the tricks about electron sharing, electron transfer, we figured them out because we started to piece these together and figured out that there were patterns to how this was assembled. This glucose is this way for reasons. And by seeing this glucose and other similar compounds, we were able to start to piece together that there is a reason underneath why it looks like this. And when we started to put that together, we were able to make predictions about what new materials should look like. Then we did the whole process. We broke them down, we studied them, we kept some of the sample, we did all the calculations, we figured out what it should look like, and we got it right. And the fact that we were able to predict what should happen and then prove it is how we knew that we had the right idea. That led us on the path to knowing that we could then explain this to new chemists who are learning how to do these things. And that's the idea. These 2 pages, 29 to 31, are showing you how chemists identify, both past and present and future, identify unknown materials. And we're going to put you to the test on that. No, I said the word test. Everyone freaks out. Not exactly. As I've mentioned in class to pretty much everybody, the plan for this particular section is that once you have finished this video lesson, it is time for you to start doing some science. Science is not information. This is knowledge. Knowledge is very important, but it is not science. Science is looking for answers. Science is uncovering the unknown in a way that is predictable and easy to share with other people. I have given you a considerable amount of knowledge over several weeks, but it is time for you to discover things with it. It is time for you to explore. So with that in mind, once you have finished this video lesson, you are prepared. Well, okay, once you have finished this lesson and done some practice, make sure you know how to do it right. Make sure to check page 32 and 33, and I think, yes, 34. There's a bunch of questions there with answers. Once you've done that, you are ready to solve your first murder mystery case. Case 1, aerial assassination. Something has gone wrong, and with the power of chemistry, you will uncover what? Maybe. If you can do it. Okay, I will leave it there, guys. Get some practice done, ask questions if you have them, and prepare to start solving some murders.